Alright students, so we are now starting with the sum of the exceptions in the periodic table. So by the exceptions we mean that if the trend will be going to like it is going to increase or it will be going to decrease, there is some variation or slight changes that decrease is not there or that increase is not there. So we are just discussing about that thing. So exceptions. So the very first property in which the exceptions is the atomic size. So first is the atomic size. So if we are moving down the group size increases. And if we are moving along the period, then size decreases. Alright. So for the group there is no exceptions, but for the period there is. So let us talk about the one period. So this is period number 2. It is given as lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. Here we will be talking about the noble gases. We know their electronic configuration as 2,1, 2,2, 2,3, 2,4, 2,5, 2,6, 2,7, 2,8. Alright. We know that atomic size decreases along the period. So it decreases along the period. So along the period the size decreases. So by this means we know that by this trend neon should be the one which is having the minimum atomic size. But the thing is fluorine is having the minimum size. And why not neon? That is because neon is having the fully filled outermost shell. So neon is having the fully filled outermost shell, that is in the second shell the maximum capacity is 8 and there are already 8 electrons present there. So this will result in a very important phenomenon known as interelectronic repulsion. So by having the fully filled shells, there arises an interelectronic repulsion, which means the electrons and electrons, they are pushing themselves away from one another. If they are moving away, it means the size will be going to increase. So here neon is having the bigger size. Alright. So what is the exception over here? That if we are moving along the period, the size will be going to decrease. But the exception is these noble gases or the inert gases which is having the fully filled shells. There arises the interelectronic repulsion by which the size will be going to increase. The trend says it should be having the minimum size, but actually the size is not minimum, it is somewhat bigger. Alright, so this was the first exception as the atomic size. Now, the second exceptions, if we are talking about the second exception, that is for the electron affinity. So that is for the electron affinity or electron gain enthalpy. Alright. So we know that electron affinity down the group, it will be going to decrease. So down the group electron affinity decreases and along the period the electron affinity increases. Alright. So along the period there is no exception. There is one exception along the group, down the group for group number 17. So for group number 17 there is exceptions. This is fluorine, chlorine, bromine, iodine, astatine. The exception is for the first two elements, that is fluorine and chlorine. If we are moving down the group, the electron affinity will decrease, but the trend is somewhat opposite. We know that for electron affinity, this is the energy released and it is represented in the negative value. For fluorine, the value is minus 327.9 kilojoule per mole. This is the value for fluorine. For chlorine, the value is minus 349 kilojoule per mole. Alright. So for chlorine, it is minus 349. For fluorine, it is minus 327. It means it is going to increase. It is increasing. This is the value and the value clearly says it is increasing. It means chlorine can easily accept the electron as compared to fluorine. Why is that going to happen? The thing is, we know when we are moving down the group, the size increases. If the atomic size increases, it means the space to accommodate that electron will be going to increase. The electron affinity is basically the tendency to gain the electron. So out of fluorine and chlorine, which will accept the electron more easily, it is chlorine, which is given by this because it is having the more energy released as compared to fluorine. Now why? Because chlorine is having the greater atomic size, so the electron which is accepted will be easily accepted as compared to fluorine. As if fluorine will accept the electron, it will again causes the interelectronic repulsion and there will be instability. So chlorine, if it is going to accept that electron, then it can easily accept on the account of its larger size and lesser interelectronic repulsion. So out of fluorine and chlorine, chlorine is having higher electron affinity. But the trend says that the down the group it should decrease. But we have seen for chlorine it increases. So that is one of the exception. Alright. So chlorine is the for the entire periodic table, chlorine is having the most electron affinity. Or the element having the maximum electron affinity, that is chlorine. Alright. So this can also be one of the questions for least and most of the periodic table. Alright. Chlorine is the element having the most or maximum electron affinity or electron gain enthalpy. Alright. So the first exception was the atomic size that we have discussed. The second is for the electron affinity. Alright. So now we'll discuss next exception. Alright. So here we'll be talking about the exceptional behavior for the ionization energy. So this is the exceptional behavior for ionization energy. So for that we'll need to understand an important concept about the shells. So we know that this is the nucleus and this is the first shell, this is the second shell, this is the third shell, like KLM shell. But this shells also consists of some subshells. Like this first shell is having one subshell as S. This 2 is having two subshells as S and P. Alright, similarly 3 is having SP, D and so on and so forth. So we are only concerned with this thing. When we are writing the electronic configuration, say we are writing the electronic configuration for lithium. So lithium is having atomic number 3, we can write it as 2, 1. Alright. First shell is fully filled according to 2n square and second shell is not fully filled. Alright. Similarly, we can write down the electronic configuration based on this subshells. So first is having the subshell only S. So this is written as 1s. First shell having subshell S. Then is second is having S and P. So it is 2s, 2p. Similarly 3s, 3p and so on and so forth. So we are only concerned with these three things, 1s, 2s and 2p. S can maximum hold 2. So this S can hold 2, this S can hold 2, P can hold 6. Alright, this is 2 and P can hold 6 electrons. Alright, this is the maximum value 2, 2 and 6. So if we are writing down the electronic configuration having 3 electrons, so this is 2 for this and 1 for this. So it is 1s2, 2s1. Alright. Now, let us talk of for the beryllium. Beryllium is 2, 2. Alright. So this is written as 1s2, 2s2. Alright. 2 and 2, 4, 2 and 2, 4. So this is how it is going to be. Similarly, if we are talking about the nitrogen, then nitrogen is having atomic number 7, which is 2, 5. It is written as 1s2, 2s2, 2p. See, 2p can hold 6 electrons. So 2 and 2, 4 and 3, 7. So this is 1s2, 2s2, 2p, 3. Similarly, for oxygen, we can write it down as 2, 6. And for that, the configuration would be 1s2, 2s2, 2p, 4. Alright. So 4 to 6 to 8. So this is how we can write down the electronic configuration based on the subshells. Now, what is this exceptional behavior? This is for the period. So if we are talking about the second period, so second period is having lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. We are just talking about this. If we are moving along the period, we know that ionization energy, it increases. Alright. So ionization energy increases as we are moving along the period. This lithium, beryllium and boron, the exceptional behavior is shown by these two and these two. What is the exceptional behavior? According to this trend, boron should be having the higher ionization energy as compared to beryllium, but it is seen that ionization energy for beryllium is higher than ionization energy for boron. Alright, so exceptional behavior is this, that ionization energy of beryllium is greater than that of boron. Now how we can say this thing? Just understand this. We are talking about the beryllium and let us just talk about the boron also. Here let me write down about boron. So lithium, beryllium, boron, so it is 2, 3 and it is written as 1s2, 2s, 2, 2p2. Alright, sorry, 2p1. So 2, 2, 4, 1, 5 and 3 to 5. So this is like this 1s2, 2s2, 2p1. Here ionization energy of beryllium is greater than boron as an exceptional behavior. Now why is this going to happen? See, if we say like for helium or for neon, the electronic configuration, this is 2 fully filled shell, this is 2, 8, both shells fully filled. Now here S can withhold 2 maximum, S can hold 2 and P can hold 6. Now you can clearly see that beryllium is having both shells fully filled, both subshells fully filled, whereas this is not fully filled. Alright, there are spaces, it can accept more electron, but these shells, they are fully filled and this is not. So ionization energy is the tendency to lose the electron. This electron can easily be lost from the P subshell, but this S, which is fully filled, it is quite stable. So it is difficult to remove this electron, and that is why we require higher ionization energy for beryllium to remove this electron from the fully filled subshell as compared to this one electron from the P subshell. So that is why the ionization energy of beryllium is greater than that of boron. Now, if we are talking of nitrogen and oxygen, according to the trend, oxygen must be having higher energy as nitrogen, but that is not the case. Ionization energy of nitrogen is much higher than ionization energy for oxygen. Now, why is that case? If we compare this thing, this is fully filled, this is fully filled, this is half fully filled, or this is half filled, because P can hold 6 electrons, but here this is partially filled, or we can say it is half filled. Half filled is also stable as compared to this, which is not half filled. So this is 1s2, 2s2 and 2p4. This is half filled. Alright, maximum is 6, it is having 3. So this is half filled. So in order to remove the electron from here is difficult as compared to removing an electron from over here. So that is why nitrogen, which is having the half filled subshell, is difficult to remove that electron. So it is having the higher ionization energy as compared to oxygen. Alright. So this was about the exceptional behavior of the ionization energy, and this concept about the subshell is required to be understood in order to understand these exceptions. In the next part, we'll discuss about an important concept known as the diagonal relationship. Alright, so now let us start with the next concept as the diagonal relationship. So this is the next concept as diagonal relationship. Now for understanding this relationship, that let us just consider two periods. So period number 2 and period number 3. And there are various groups. So hydrogen, helium, period 2 starts with lithium. There is beryllium, let me write it over here, beryllium, boron, carbon, nitrogen, oxygen, so on and so forth. So this is fluorine, neon, so this is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Now the property which helps us to understand the you would say diagonal relationship is electronegativity. Now, electronegativity is a tendency to attract the shared pair of electron towards itself. If someone is incapable of doing so, it means that is metal. If someone is capable of doing that, so it means it is a non-metal. So we are taking the criteria about the electronegativity. And if the difference of the electronegativity of the two elements is very, very less, it means they will behave almost same. So if the electronegativity difference is less, so it means they both are either metals or non-metals, but there will be some relationship between that thing. So we know that electronegativity, it, you would say, increases along the period and decreases down the group. So this is the thing that we have already discussed. So electronegativity increases along the period and decreases down the group. So if we'll take this into consideration, so if lithium is having some electronegativity, the electronegativity, it increases along the period. So it means beryllium is having somewhat higher electronegativity than lithium. But now if I am moving towards the group, it means magnesium is having lesser electronegativity as compared to beryllium, because down the group it decreases. So the difference between the electronegativity for lithium and magnesium is very, very less. For lithium and magnesium, the electronegativity difference is very, very less. So it means they will resemble in their properties, forming a diagonal relationship. So lithium and magnesium, they will show some similar properties because of this diagonal relationship or least electronegativity difference. If we are moving from beryllium to boron, electronegativity increases. For aluminium, it decreases. Beryllium and aluminium will show similar electronegativity, or it would be, you would say, somewhat similar, not exactly. So I can say electronegativity difference is less. So beryllium and aluminium, this is going to be act as a diagonal relationship. Similarly, this can also be happen with boron and silicon. Alright. So the elements which are present along the diagonal, they will show some properties which are similar to that. So this is the diagonal relationship. And the elements like lithium and magnesium, beryllium and aluminium, this group which they have formed, this pair, they are known as bridge elements. They are known as bridge elements. Now the thing is, they are having very less electronegativity difference. The difference between the electronegativity is very, very less. That is why they are showing this diagonal relationship, and these elements, they are known as bridge elements. Alright. So this was all about the diagonal relationship, and by this we have come to the end of this chapter as the modern periodic table.